Hi, everybody. I'm Dustin Schroeder. I'm a associate professor in the geophysics and electrical engineering departments at Stanford. And my talk, I'll try to cover a few things. One, I'm a member of the TIME project as part of ITGC. And we've, as we've navigated COVID delays, done a bit of technology development that I'm happy to share here. I'm also thrilled that so many, collaborators are on the call. I see Scott Kempf is here from UTIG, who, when I was a grad student, I learned a lot of the basis of what I've done here from, and others who we collaborate with. So this talk, I think most ideally would have been given by my graduate student, Anna Broom, but she's going down to time now, and so was not able to give this presentation. So what you're going to kind of get is Anna's talk sandwiched in between some framing comments from me, and I'll try and cover each of the technologies that are relevant to the TIME project, and then during the discussion we can touch on whatever is interesting to you. Many people here will not need an introduction to ice penetrating radar. For those of you who don't normally look at it, what we're talking about is radar pulses that go down through the ice sheet, typically collected from airplanes, but not what I'm going to talk about today. The pulses come back and you get profiles like that. People mostly make maps of what the ice sheet looks like on the bottom, or look at these profiles and think about doing sort of structural glaciology with those profiles. A lot of what I'm going to talk about now is interpreting the radiometric signal, how bright a reflection is. And so the two things that tend to control that and are relevant for here, if you get a bright reflection from the bottom, like that top left corner, it could be because the reflection coefficient from the bottom is high. You see that table in the bottom ranges over 40 dB, that's 10 to the fourth. So you get 10,000 times variation in brightness depending on the material. It also depends a lot on temperature. You see the curve in the top right. The warmer it gets, the more rapidly it absorbs energy, and that ranges from 1 dB per kilometer to like 50 dB per kilometer. So these are big old knobs being turned as the ice gets warmer or colder, wet or drier on the bottom. And as a community of radioglaciologists, we study all sorts of things inside the ice sheet using those signals. Now, in the context of time is about the eastern shear margin of Thwaites. And actually, Joe's paper from when I was a grad student is significant motivation for this. So if you look at all these shear margins of Thwaites, you see the eastern shear margin there in the circle. Most of those black lines, which are shear margins, you could imagine drawing if you saw the topography, high topography there, you draw all those other lines. This one goes across high topography. There's not a strong topographic explanation of why the margin is there. And I mean, that's interesting. It's between two of the fastest changing, most potentially unstabilist glaciers we have. So we'd like to know why it is where it is. Some early work I did looked at the reflection coefficient between the outside and the inside is brighter. There's a chicken and an egg situation there. Is it brighter because it's wet and therefore that's why it's going faster, or is it going faster and it produces melt and that's why it's wet and that's why it's brighter? So we don't really solve the why it's there and how stable is it question. The TIME project is zooming in on this margin and trying to understand that deeply. And there's a couple hypotheses that are really specific and have shaped the technology development we've done. So one of the hypotheses is that the shear margin itself is warm, and there's this warm piece of the ice in the margin, and that's important for why it is where it is. And so in this case, actually, my former PhD student, Nicole Beinert, who's now at Google, developed a system based on, I see Lai Bun is on the call, based on Lai Bun's lock system, the PRES, which stayed out 1 point. And she developed a software-defined radio system that listened to that system and then coherently synchronized itself and allowed offsets of kilometers. And so if you're thinking about the tomography you could do, having all those variable angles through it, you can do much better by having a much larger offset. She also showed that, contrary to previous belief, there is no total internal reflection limit in terms of the offset you can get if you're on the surface, because you get coupling between those antennas. Maybe my favorite thing that came out of her final paper is in the bottom right, that actually if you take that bistatic system and then take two separate polarizations, you can see those reflection curves on the bottom, that actually the dielectric property of the bed itself is extremely diagnostic, where it drops off and you get no return. She was doing this to show, hey, don't set up your antennas wrong because then you won't get a return. But actually that lack of a return gives you very strong constraints on those material properties. The other thing that we're interested in is the fabric of the ice itself. And again, by doing these polarimetric observations, you can constrain that. Now there's ambiguity like others have done when you look down with polarimetric radar, But if you, again, do these bistatic polarimetric measurements, you can also look at the off-nadir axis of the crystal fabric as well. So this is one flavor of technology development we've done. Now, we've had a bunch of delays like everybody else. And a lot of these experiments, when we go down, we're shorter and we spend a lot of time digging up 2 years worth of snow on top of our instruments. And so as a result, there's been a necessity-driven creative enterprise. So my youngest PhD student, Danny, is looking at airborne data and looking at the hyperbole from unfocused data on the bed, trying to do demography with those off-nadir echoes. And TJ Young, who's a postdoc on the project, was looking at single polarization data from the air and seeing these interference fringes you can see on the top right, and looking at that birefringent effect of those fringes to try and get polarimetric constraints on the fabric without having a polarimetric radar. So this is not technology development as much as sort of like Luddite creativity with what we happen to have. Now, okay, that's there. Now, like I said, this would have been Anna's talk, I think, in an ideal world. She's going down to Thwaites now, and Anna's building a ground-based system that's trying to allow you to make really fine scale constraints on bed conditions. So her initial paper was on getting sort of radically multi-frequency data. And what she showed here is, if you look at the top right in those cartoons, maybe the bed's more reflective because it's flat. Maybe it's more reflective because the material property is more contrasting. There's ambiguity if you have one frequency. If you want to break that ambiguity, what you can do is you can have really varied frequencies, and the reflectivity of the material is not going to vary as quickly with frequency as the roughness will. And so what she shows on the bottom left is if you have a single frequency, if you make no other assumption, there's a lot of ambiguity in that material property. As you move to multiband, and multiband, we're talking 1, 10, 100 megahertz. This is very broad. You get much better constraints. And finally, if you really work on implementing your radar kind of like a radiometer, where your radiometric precision is better, then you can really constrain this. Now, we've built on this, and I see Joel Johnson's on the call as well, and we've had the pleasure of working with Joel and trying to develop a system into a hybrid active-passive system. And so the idea here is that another ambiguity we're trying to correct is the attenuation in the ice. And could we build a radiometer that sits on a sled and gets constraints both ways? So the radar, what it does is it experiences the two-way temperature-dependent attenuation, as we talked about in the beginning. And that's the attenuation, but it's the round trip, one measurement, one scalar value. The radiometer looks at both that attenuation and the emissions as a function of temperature. And so it's measuring some of the same things and some of the other things it's not. Now, the radiometer tends to be more sensitive near the surface because you're counting on those emissions making it through the ice. And some of the warmest pieces near the bottom, because the warmer it gets, the more there's attenuation, it sometimes struggles to directly measure those deeper temperatures, and you're dependent on what you would call a model-based retrieval to get deeper. The radar measures through the whole thing, but again, no profile, just one scalar value. So Anna's work is to say, how can we combine these two together to make a stronger combined constraint on this? So she goes through and says, okay, we're going to have a polarimetric system that will constrain birefringence. We're about to do this for the attenuation. And then all that's left is the reflectivity, which we just said we can separate roughness and material properties. So that's great. So she goes through initially and says, okay, let's start and say, can we correct, for the purpose of correcting attenuation, how good does the radiometer need to be? And so for areas where you have a nice radiometer-friendly temperature profile, it's great. The radiometer does a great job with its model-based retrieval of the temperature with depth, and you can see these temperature errors on the right get small, and it does a great job of correcting the attenuation. And the types of attenuation errors you get from this implementation is a couple of dB. And again, we said the signal in the beginning is like 40 dB or even 10 dB. A couple dB is pretty good. So for a sort of well-behaved setting where the radiometer is having a nice time of it, adding it there is going to do great. And it's even going to do greater because for those cold temperatures, the effect on attenuation isn't that big. Now we think about saying, okay, what about if we're interested in the temperature in and of itself? How can we use these two systems together? And so this starts to help a lot where you say, okay, if you do a joint retrieval where you simulate lots of different temperature profiles and you say, what is consistent with the brightness temperatures you measure with the radiometer, and then also consistent with that two-way attenuation from the radar, as you can see, you start to get much finer constraints, and it's easier. Zoom window sort of blocking my view of my own slides. Okay, but what you can see here is on the radiometer configuration itself on the top, you have, especially as you get deep, these big wide swaths, like the bed temperature in the radiometer itself there, plus and -20 to 10. But as you combine it with the radar, you get much finer constraints in those distributions, right? And it's because the radar is directly measuring that higher attenuation near the bed. You say, okay, what would this look like? We put it on the surface. There's an insight beyond just like, okay, are we building a giant sort of downward facing radio telescope, swanky radiometer and swanky radar? And one of the things she also has shown is that actually you can back off a lot on the demands of the radiometer, one, by using the radar together, and two, by implementing it on the ground. So in this case, she's saying, okay, if we have a nice, 12-channel radiometer that gives you the constraints on the left, and it performs pretty similarly to the radar plus radiometer. These are both have radar plus radiometer with fewer channels. It's because the radar is doing a lot of work for you. So you're now not counting on that radiometer to get deeper and deeper to constrain that temperature profile and use the physics to get you down to the bed. So that's one massive relaxation in the system demands. Another system demand relaxation is actually in terms of the radiometric resolution itself, right? You can see that these constraints, especially if you look at the bed, yeah, it does improve as you start to beat down the radiometric resolution, but actually even with these very achievable values on the left, the constraints still way better than sort of a radiometer alone system, and certainly better than a radar alone system, which is deeply ambiguous if you don't pin that temperature on the surface. The other thing she's shown is that you don't need a highly directive antenna. So this also, because you're on the surface, you can imagine, you're staring down, right? Like if you had a camera and you're trying to, estimate the color of some leaves on a tree, you might need like good resolution. But if you like just shove your face in the tree where you're just like in the leaves, like you're going to see the leaves no matter how directive your camera is. And so the same thing, you're on the ice surface, you're looking all the way out there, you're seeing everything with the radiometer and radar. So that makes it easier as well. So in the spirit of bridging the Arctic and Antarctic, as our field seasons have been canceled and downscoped and delayed, we've done some testing initially in Svalbard and then in Iceland. And then the reason Anna's not here, she's preparing to go down to the TIME project and test this in Antarctica this year, and then again next year. So that's the pitch on Anna's stuff. The final thing I'll add, which is not related to Thwaites, but is related to technology, is like many groups are developing drones. And my other student, Thomas, who you might want to invite for a future one of these, is developing these fixed wings radar sounding drones. So these again were COVID development efforts. So the initial efforts required the hardest permit we got, which was the permit to fly these things on Stanford's campus. But during the pandemic, that's where we were limited. So we did these initial tests on campus. Then in the top right, we've been going to Iceland and testing it. And you have from our sort of entry level, smallest radar, the data from Iceland just collected a couple months ago, and there in the top right. And then this is part of a family of ever increasingly capable in terms of duration and performance systems. So they're all named after our falcons or birds. So this is the peregrine system, which you throw by hand and has a sort of 56 megahertz bandwidth chirp. It has about 25-kilometer autonomous surveying. You just throw it, it flies in and comes back to you. And so this is the entry-level version, which does exist and has collected that data. So that was a quick whirlwind, but I also didn't know what people's interest would be on the call. So hopefully you find something in there that's of interest to you. Thanks again for having me.
Awesome. Thank you, Dusty. Any quick questions for Dusty before we proceed? I've got a
question, Joe.
Oh, go for it. Go for it, Luke.
Cool talk, Dusty. My question is about when you use those multi-frequency radars and you're trying to infer differences in the bed composition or the roughness, how does like the entrainment of like debris in the basal ice complicate that? Will it mask itself as roughness or composition or both? Or
I mean, that's a deeply unpleasant question to engage with. So it really depends how thick it is, how warm it is. I think, if the entrained sediment is electrically conductive at all and it is wet at all, it can dominate things. So you could imagine a world where that was conductive enough that what you're seeing is the top of that water sediment layer. And as a totally nerdy aside, we have this in the community, this gap that we see lakes in radar data, and then we see lakes in altimetry, and very few do we see in both. And one of the hypotheses that I have for why that may be is as for these active lakes that are pumping up and down, if you're injecting up water into the ice that has some sediment in it that's conductive at all, maybe all you ever see is the top of that injected water. And so that's one potential explanation there. Another potential explanation or effect would be if you had a gradient of those sediments and a gradient in that water. Reflections come from sharp interfaces. You have that gradient, and it actually could be like a cloaking device for the bed. So that's a different effect there. If it's frozen and cold and the sediments are in there and they're, say, big rocky sediments, then it's going to look like roughness. But I think it could be each one of those. What the hope would be is with these really wide frequency dependencies, you could still, I mean, you can't have it every way and use the same information in different ways, but it's going to be way information richer. And say it was cold and rough, you would see a strong frequency dependent effect. If it's a material property, you would see a different effect, maybe a polarization effect. So I still think this more information rich system can help you, but it's not going to be clean in the way I just showed in terms of 2 axes roughness material.
Great, thanks.
Okay, great question. And speaking of sediment, I think that might help us lead into the next talk. So thank you, Luke and Dusty, for that transition. Next up, we'll move on to Ryan Venturelli from Colorado School of Mines. And Ryan, would you like to introduce yourself a little more and share your screen?
Are you seeing my slides? Or
Yep.
my presenter view? Okay, cool. Thanks, Joe, for that introduction. Hi, everyone. It's great to be here today to talk with you all about things going on at the base of Thwaites Glacier and how we can use sub-ice drilling technology to obtain geological constraints on past grounding line retreat. So I'm Ryan Venturelli. I'm a new assistant professor at Colorado School of Mines. And my part of the International Thwaites Glacier collaboration is called Geological History Constraints. And we seek to use the geological record to tell us about what happened to glaciers in the Amundsen Sea embayment before we started watching. Of course, I'm the person talking to you today, but this work would not be possible without funding from NSF and support from IDP. It's great to see all of the IDP folks on the call today. They know a whole lot more about this drilling system than I do, so hopefully they'll be able to answer your questions. Okay, so typically when we think about what happened to glaciers and ice sheets before we started watching, we use either the marine geological record or the exposed geological record. So for the last few decades, we've been collecting bedrock and erratic samples from exposed rock surfaces that poke out above the ice sheet and applying cosmogenic nuclide exposure dating to tell us when ice retreated from that area. And in doing this, we have amassed a really great, at least circum-west Antarctic data set that tells us about what happened since the last glacial maximum around West Antarctica. So what I'm showing you here is a record of all of the exposure dating arrays that have at least 3 Holocene time exposure times in the data set, with the places noted in colored squares telling us about times where our glacial geologic record stops somewhere after about 5,000 years ago. Places where I show you glacial geologic records with a colored circle give us kind of the glacial geologic history right up until our observational record starts. So when we look at all of these data around Antarctica, we interpret these colored boxes to mean that there has either been zero change in ice thickness at these locations over the last several thousand years, or this site can experienced continued thinning below the present ice surface, followed by thickening to present conditions. And really understanding whether or not the ice was stable for a period of a few thousand years, or deglaciation since the last glacial maximum continued past that, is really important for building a time series of glacial change to connect with our modern observations. We think it's probably pretty unlikely that there was zero change in ice thickness for a period of several thousand years, because we just know that the surface of the ice is more dynamic than that. So our hypothesis then is that anywhere that these time gaps exist could be a marker for grounding line retreat and readvance in the Holocene. This phenomenon occurs in the Amundsen Sea embayment. So we have both on the Thwaites Glacier side and the Pine Island Glacier side, a gap in our geologic record from about 6,000 years to present. So this offered a really great place to test the hypothesis of retreat and readvance. And of course, this means that any evidence for further thinning and retreat is hidden beneath the cover of modern ice, and we need a drill to get us there. So the big question that we are asking as part of GHC is, were glaciers in the Amundsen Sea embayment less extensive than they are today in the recent geologic past? And what were the boundary conditions that enabled recovery from that smaller or less extensive state in the last few thousand years? So we, the only place where there is exposed rock in the Thwaites Glacier area is the Mount Murphy Massif, which is a volcanic edifice between Thwaites and Pope glaciers. And we use the most grounding line proximal ridge to test this hypothesis. So Seth Campbell, as part of the GHC team, shot radar on the subglacial extension of the K Peak Ridge to locate where that ridge extended to beneath the ice so that we could find where to drill our hole. And to get through the ice and into the bedrock, IDP uses the Eclipse drill for three reasons. It leaves an almost perfectly clean hole, which is different than augering technology that is a little bit messier and could leave behind large ice chips in the borehole. The Eclipse drill is a standalone system and can be operated simultaneously with the Winky drill, which I'll tell you about next. And it enables us to take firm density measurements that can be made with recovered cores. And this is really important for the application of cosmogenic nuclides because it allows us to constrain shielding with ice cover and changing ice through time. And kind of an unexpected bonus of using the Eclipse drill to gain access into our borehole was that we could do a whole bunch of extra and unplanned science. So these are two undergraduate students that we were able to bring onto the project because we collected a bonus ice core above our bedrock core site. Their names are Nia Duncan and Garrett Gillard. They are at Binghamton University and Savannah State. And what they did as part of this project was use this ice core of opportunity to generate a stable isotope record to give us baseline data for future coastal ice scoring efforts. And when we think about connecting the records that we are generating from subglacial bedrock with environmental reconstructions and paleoclimate reconstructions, this baseline data will be really, really useful for telling us where to go next to core coastal ice domes. So once we gain our access hole with the Eclipse drill, we use the Winky drill to drill into the bedrock. So the Winky drill is the lightest rock sampling drill in the IDP arsenal. It uses conventional rotary coring techniques common throughout mineral exploration, and a drill string of jointed pipes that can be advanced through the access hole into the glacier and collect bedrock samples below. We use bit cooling and chip transport with forward circulation, and it employs conventional coring rather than wireline coring. So here's a schematic from Grant Beckman's paper published in 2021. I'll give you the citation for that later. That shows how this Winky drill works. It's composed of three main subsystems: the drill rig and power head, the downhole tooling, and the circulation and filtration system. And what it looks like in real life as we're drilling into bedrock out in front of a nunatak is shown here on the right. So here are some pictures of the ice bits and drill bits used to drill into subglacial bedrock using the Winky drill. The ice bit shown on the leftmost part of the slide is designed to advance a borehole through clear ice and the bedrock below by chipping the full diameter of ice and transporting that away. And then the bits shown next to that are the 4 bits that the Winky drill is equipped with. So first is the diamond impregnated bit, which is used to drill through hard bedrock. The geoset bit is used in soft rock formations or when there are sediments entrained in the base of the ice. The PDC can be used in soft rock formations, but has had limited success when ice is present. And there's also a hybrid impregnated bit shown here on the bottom. The purpose of the drill fluid is really to cool the bit and flush chips away to the surface so that fluid can be filtered and recycled in the closed loop system. And a schematic of that system is shown on the rightmost portion of my slide. So all of the details of the deployment of the Winky drill for subglacial bedrock sampling in Antarctica are published in Grant Beckman's 2021 paper. So I encourage you all to read that if you're interested in subglacial bedrock sampling. It really chronicles what happened at the K-Peak site and other deployments of the Winky drill in Antarctica. And I also want to encourage you to look at the IDP website, which really details their full suite of tools and what we can do with all of them. So to talk a little bit about the success and the science that we were able to do because of this technology, I just want to highlight that we drilled 6 access holes, 4 core holes, and recovered 3 bedrock cores ranging from 1.2 to 1.4 meters long. And because of this really amazing recovery, we were able to use all of the quartz in all of this beautiful biotite gneiss bedrock to give us a lot of opportunity for cosmogenic nuclide measurements to give us a really good idea of what happened in this region before we started watching. And shown here on the left is just how these core holes all relate to one another. So we took multiple bedrock cores so that we could have kind of a transect down ridge beneath ice of increasing thickness with depth. And we paired the cosmogenic nuclide measurements that we made with a forward model of ice history that basically generated simulated ice histories that could possibly reproduce the cosmogenic nuclide measurements that we made. And what I'm showing here on the rightmost panel of this figure is a thinning history from about 9,000 years ago to present. The modern ice surface is shown with this black horizontal line, and all of the green lines are ice histories that reproduce cosmogenic nuclide profiles that match our measurements. So in every case, at every hole with both beryllium-10 and carbon-14, which are able to constrain what happened over the last few thousand years, we find that ice was thinner in this region by about 30 to 35 meters for a period of 3,000 years before ice rethickened somewhere in the last 2,000 years to where we observe it today. So to bring this back to that time gap, this tells us that ice continued deglaciating at Thwaites Glacier for several thousand years after we originally thought, because of that surface exposure record, and recovered sometime in the recent geologic past. And we're able to connect the thinning of about 30 to 35 meters with grounding line retreat of about tens of kilometers in this area, because we know, because we have an observational record of ice thinning and grounding line retreat. So in these two images shown here on the right, I have an aerial photograph from 1966 and a worldview image from 2018, which shows thinning of about 30 meters over this area associated with the grounding line retreat that we observe in our modern record. So this talk was kind of a mix of the really cool things we can do with subglacial bedrock drilling and the science that comes out of it. But what I really want you to take home from me presenting here, a geologist talking to a lot of people interested in technology, is that the Winky drill was able to collect significant scientific samples during deployment as part of ITGC. We found an episode of thinning near Thwaites and Pope glaciers in the late Holocene that demonstrates kind of the reversibility of ice retreat and ice sheet thinning under climate conditions similar to today, and really connecting these the ongoing paleoclimate efforts with this paleoglaciological reconstruction will really help us to constrain the reversibility of retreat around Antarctica. And I think that something really exciting as a geologist and as a paleoglaciologist is that the advance in sub-ice access drilling really enables us to push the needle forward in my field, such that we can generate a more continuous record of glacial change from before we started watching. And this will allow us to connect these paleo records with the records that we are observing today, so that we can gain a more holistic view of long-term ice sheet processes. More on this paper and the deployment of the Winky drill can be found in our paper that is in review in the cryosphere. So if you scan this QR code in the corner of my slide, you can just download the paper right to your phone. And stay tuned, because we also were one of the groups that had a lot of delays, but we will be drilling at a nunatak on the Pine Island side of the Amundsen Sea embayment called Winky Nunatak, which actually is named after the drill because of the great work that it did for us on GHC. Thanks for your attention, and I look forward to discussing with you.
Awesome. Thank you, Ryan. I know I learned quite a bit. I imagine other folks did too. Yeah. I certainly have some questions. Are there any other folks who want to chime in initially? Maybe I'll ask. Oh, Jack, go ahead.
I was just wondering, Ryan, or maybe somebody from IDP, to make this work, to get the chips and the fluid out, do you have to case the full depth of the hole? It wasn't clear. It said you could or couldn't. Sometimes you put casing in if you wanted to, or is that a requirement to actually drill in fluid and get the chips out?
We do use casing. I see Chrissy and Elliot on the call if they want to give all the dirty details of that.
Sure, yeah, I can jump in here.
Thanks, Elliot.
Typically, we have to case to just below the firn ice transition, and that's so we're not losing fluid while drilling. It's usually easiest to get the access hole as close as we can to bedrock with the Eclipse drill, and then from there take it with the Winky drill. The Eclipse drill is a lot better at making a clean borehole than the Winky drill, so that's usually our procedure there.
Thanks.
Ryan, I'm wondering, so the Winky drill can go up to 120 meters, I think it showed in the abstract. So is there a way of taking that depth limit and what we know about topography so far around the ice sheet and how much ice sheet models disagree in certain locations to pick your favorite next spots, realizing that many ice sheet models may not resolve some of these nunataks, sadly. But how do you go about picking the next places you want to start filling in that record? Is maybe the better way of broadly asking that question.
Yeah, that's a great question, Joe. Thanks. So I'll start with the first part of your question that was thinking about depth of coring. Drilling deeper into the bedrock, at least for questions of what happened since like through the last deglaciation, won't necessarily happen or won't necessarily help us because the cosmogenic nuclides accumulate in the topmost part of that bedrock, and then that signal decreases down core. But drilling through thicker ice could help us on kind of different timescales. So if we're thinking about like ice collapse during the last interglacial or something, we would want to go to a much more deeply buried area of the ice sheet. These what we're working with here at Cape Peak and this upcoming season at Winky Nunatak, we're looking at like tens of meters. We don't want to go much more than 100 meters around kind of the edges of the ice sheet because it's not likely that we had like full collapse or deglaciation greater than that. So it would be diminishing returns for drilling through more ice. And then for thinking about where to go next, I think with an N=1, we've gotten some really promising results from Cape Peak, and it meshed really well with the hypothesis that the time gap represents that more deglaciation continued happening in this area. So I think going to the nunataks that we have had an opportunity to sample and have like a really rich elevation transect that stops anywhere from 7,000 to 5,000 years ago, that has a subglacial extension of that nunatak with ice thinner than 100 meters. Those are kind of the best places to go to figure out if this if the time gap tells us the same thing everywhere. So and then I think what will be even more interesting than finding retreat and readvance at a place like Thwaites is finding where we don't get retreat and readvance and using the difference in continued deglaciation and the stopping of deglaciation to inform us about what we can expect of the future and where we'll go, where we will retreat to inland in the future. So that was a really long answer, but I hope I answered your question.
No, that does help. And that last point that you raised where retreat and readvance seems to be more part of the Holocene story than have maybe been imagined 2 decades ago for the waste. So are there any places that do actually just straight up monotonically retreat left to understand? Forgive my naivete if I'm misinterpreting the data, but yeah.
So there are, I'm going to share my screen again to show you that map that I originally showed. No matter how long I've been sharing screens, this still pains me to do. So let me get my laser pointer. So we have something actually kind of weird happening. So we know from other work that I'm involved in and work that Johnny Kingsley published on in 2018, that there is sufficient evidence on the Sipal coast of the Ross Embayment that the grounding line retreated inland and re-advanced. But we have all of these records in the southern Transantarctic mountains. So these like 1 through 5, which are boxes 1 through 5 here on the bottom part of this plot, that actually have a record of deglaciation that that ends right kind of in the modern. So this tells us that we had that kind of monotonic, slower retreat and no real evidence for re-advance here in the southern Transantarctics, but we did have it in the Sipal coast. So I think that this is like a really interesting conundrum that will help us understand kind of the differences in forcing between retreat and re-advance and stopping retreat. And it could just be a matter of this being a really flat area along the Sipal coast and us retreating kind of into the Transantarctics being a different style of retreat, but there's still a lot to learn there. And that's another really interesting thing to me. So.
Awesome. Thank you for that clarification. Looks like Jack has another question.
Yeah, I was just thinking about, it's really exciting what you're doing, but do you really need to have the altitude gradient in the subaerially exposed rocks? I mean, couldn't you just go everywhere right along 3 feet from the current position of the ice sheet and see what the exposure age there is? And if it's thousands of years old, then you got a candidate, right? And you could do a survey with much less analysis, I guess is my question.
Yes, you can.
Less cost and less, quicker.
Yeah, that's a good point of cost benefit analysis, but the real benefit to the elevation transect gets at kind of the rate of retreat from like a much thicker ice sheet to today, and getting at the style rather than just like when retreat happened helps us to think about kind of deglaciation as a process, not deglaciation as an archive. But you're right that we could find that time gap with just kind of the ice surface as well.
Right. I mean, if you were trying to figure out places where it'd be interesting to go out there and drill through the ice sheet to get sub ice, all you need is to know that right now at the ice margin, there's an age gap of some thousands of years, or there isn't, right? And you'd rule out a lot of places not to bother with.
Yeah.
Great. Thanks, guys. Any additional questions? I've still got more, but I don't want to dominate the questioning. I have a question that might merge the two of you, if you haven't already thought about it. I love, Dusty, I have a question for you. I know that you've worked on merging software between your radiometer radar concept, which is awesome. And I look forward to hearing more about that, and the UAVs. Is it possible technically to combine the radiometer radar concept on the UAV as well, or is there a sampling challenge there that I maybe misunderstand?
I don't know that it's a sampling challenge, but I think the progress both Anna and Thomas are making, I think, partially come from embracing the strengths and limitations of their platforms. Mm-hmm. And so I think for Anna, being on the ground and being able to move antennas around and being able to have long antennas or separate channels, or to not have to worry about effects on the surface and to be moving slowly and to have not infinite power, but plenty of power. All those things make implementing stuff efficiently work better than a totally general purpose implementation. Similarly with Thomas, I think, one of the things I admire about the approach he chose to take, he worked for a drone startup that delivered medicine in remote environments between undergrad and grad school. And I think he leaned into these shorter duration platforms that we could prototype quickly, that were the Peregrine model is actually made out of styrofoam, so it's non-conductive, which is important. Makes integrating the antenna easier. Payload small. There's a lot that he developed that really leaned into that. And I think as you start to move towards things that do more, that's an engineering challenge, and often the sort of efficiency or speed or elegance with which we're able to implement it gets compromised by that more general purpose. So that's the short answer of like our platforms as they exist. I think there's a total separate piece where so there's Anna as radar instrument architect and engineer, and then there's Anna as a geophysicist, and I would say that her insights into the radiometer constraint on the shallow ice and sounder constraint deeper, I think that is very portable to existing airborne instruments. Joel's on the call. I think if you're talking about combining ice bridge type data and UWB-RAD from the air, I think there's interesting ways to think about moving it to satellites. I think that geophysical insight of her approach is very portable and rich, but I think on our platforms, those instruments are deeply different in weight, size, and cumbersomeness that would make it a challenge.
Yeah, that's fair. That's helpful. Then maybe trying to combine the two of you, could the Peregrine have done at UHF the survey, the GPR survey that's needed for site selection for Ryan's locations?
I think
it certainly looked like it from that grid you showed.
I
which was
think
awesome.
it's immense. I think it's immensely possible. I think, again, necessity has shaped the way we develop, but because our field testing has happened in Iceland, where there's a lot of wet, nasty stuff in the near surface, we've done a lot of our initial development with it as sort of a near surface object. And so I think we have a lot of confidence that it would fare well in those environments.
Yeah, I think it could really streamline field operations, because when we're thinking about getting out to these sites, building a remote camp, setting up a drill and drilling through the ice, like any small bit of weather delays or transport delays to our site cut down our available time for sampling significantly. And to have to conduct like a ground-based survey, process all those data, figure out where the drill site will be, can be a really big chunk of time. So I see like Dusty and Thomas's work with the drone development to be something that could work really well in helping us more efficiently generate these records that are otherwise really hard and time consuming to get.
Yeah, absolutely. Yeah. Great, thanks. Any other questions from folks on the call? This is very exciting. I want to see it in the Arctic next year. All right, great. Well, thank you, Dusty. Thank you, Ryan. Thank you, Meredith, and all the other co-leads for helping to organize it. This was very interesting and excited. Man, Thwaites does not give up its secrets easily, but I'm excited to see what you guys are learning and will continue to learn. So thank you so much.
So Joe, I was surprised Dusty didn't pipe up. He's trying to bring these systems up to Summit for more testing. No real hard driving science questions, but some testing and to get the thermal structure of the inland Greenland ice sheet. Hopefully.
Yeah, that's correct. Yes. So in the Arctic, we are supplicants. Yes, please give us resources and a flight, and we'll measure your cold, boring ice column.
That's where the best stuff is, the cold, boring ice. All right. Be well, everyone. And thank you again. And we'll see you again, either in the ether or in person. Be well.
Hey, Joe.
Thank you.